Alright, a load P is applied to a beam that's joined to a column with 4 rivets. The moment arm from P to the hole pattern centroid is L. We want to find the required rivet diameter to withstand the shear loads. If P is 4,500 newtons, L is a half meter, and the hole pattern is 0.1 meters square. We're given a rivet shear strength of 65.25 megapascals, and we want a safety factor of 2. And so the first thing that we need to do, according to our procedure, is we need to label these holes. We don't probably need to, but why not? A, B, C, and D. All right. And we need to find the centroid of the hole pattern. So let's see. First, here on the left, we've got P, and we've got our 4 rivets holding the little plate onto the vertical column there. We have a free body diagram of the beam itself here on the right. So we show our applied load P, and the 4 rivets or bolts collectively have to generate an equal and opposite force V, which is, we're calling it V on purpose. It's basically resisting the direct shear downward force P. P times L is going to create a moment, and the 4 rivets have to collectively create an equal and opposite moment M. So let's expand the bolt pattern here. The centroid is pretty easy to find. This is a square with length side L, and each of the distances from the centroid, which is right in the middle, each of the distances from the centroid to the rivet is going to be L over 2 squared plus L over 2 squared, square root of, ends up being L over root 2. All right, so all of the distances from the centroid to the rivets are the same. All right, so the procedure says determine the centroid of the hole pattern, find the moment M of the applied load about the centroid, which we've essentially done. That moment M is equal to P times L. We're assuming that the shear load is distributed evenly over all 4 rivets, so even if some local yielding has to occur because of hole sloppiness, eventually all 4 will take the same load. For rivet I being 1 to 4 here, calculate the direct shear force. And the direct shear force is very straightforward. It's simply, we're going to call that F prime. Okay, so F prime in rivets A, B, C, and D, it's going to be the same, and it's going to be the total force P divided by the number of rivets. So I'll call lowercase n here. Alright, so that's the direct shear force. Next, the procedure says, draw those direct shear forces on the appropriate holes in the shear load location. This is an FBD of the portion of the rivet in the top plate. So when we push down on the top plate, the rivets are going to push up on the top plate, and the plate is going to push down on the rivets. So we're going to have our F prime forces coming straight down, and they're all basically going to be the same there. Okay, and I have FD prime. All right. Next, calculate the distances from the centroid to holes A, B, C, and D. We've got that done. Next, draw the moment forces F double prime at hole A, perpendicular to RA, at hole B, perpendicular to hole B, etc. So the assumption here is that we're trying to create this moment M. All right. Now, there's a tendency for the plate to want to rotate this way. The rivets are going to create a moment on the plate which is counterclockwise as shown there. That means that the plate creates an equal and opposite moment on the rivets, which is going to be clockwise. Imagine if you were to rotate this plate about the centroid. This hole would want to gravitate over here. This hole would want to gravitate over here. And the rivets, well, they're going to want to stay put. Okay? So the rivets are going to end up creating forces on the top plate which are going to be basically perpendicular to these lines RA, RB, RC, and RD. Okay. So we can imagine rivet A encountering what I'm going to call an F double prime force, perpendicular. I'm going to draw an FB double prime and an FD double prime. Now, the thing about these forces is they're not automatically going to be all equal to each other. The direct shear forces were all equal to each other, but not necessarily the F double prime forces. Okay, and the reason is because these double prime forces are proportional to the distance from the centroid. So down here, force F double prime on an individual rivet is directly proportional to the distance of the hole from the centroid. So if this joint was actually pinned at the centroid, imagine if we had a long, thin bar. Imagine it had a couple of holes in it. Imagine that these were holes A and B, and they're not for this example up here. This is just for illustrative purposes. So there'd be your rivets. Now suppose you apply a moment that wants to rotate that bar about the centroid. That bar would end up wanting to move sort of like this. Okay, it would want to rotate. And the holes would want to go to those locations shown. Okay? And if the holes did gravitate a little bit, they would cause some strain in the rivets. So this would be strain due to the rotation that would arise from that moment. And we can see that the farther we are from the pivot point, the more strain there is. If you're twice as far away, there's twice as much strain. All right? And if there's twice as much strain, and we're still in the elastic zone, then there must be twice as much stress. And if there's twice as much stress and all the rivets have the same diameter, then there must be twice as much force. All right, so I'll make a little note here. Farther from pivot equals more strain, which equals more stress, which equals more of this F double prime force. All right. So just to summarize here, before we do a derivation of the expression for F double prime on the next page, we have our direct shear forces listed, and then we also have the shear forces that create the moment. M equals PL. And again, they're not necessarily equal. They will be in this case because they're all the same distance from the centroid. Now the procedure gives a formula for finding them. It says F double prime I is the moment times the distance of that rivet from the centroid times the sum of all the distances squared. Okay, now where does that come from? Well, let's look at our example. Direct shear force components. Okay, we said FA prime equals FB prime equals FC prime equals FD prime equals total shear force over, or I should say, external applied force in the shear plane divided by the number of bolts. In our example, we said P was 4,500 newtons, and it was divided by 4 bolts. So we have 1,125 newtons straight down. Okay, now the torsion type force components that create the moment. Let's see, what do we got here? We've got FA double prime, FB double prime, FC double prime, and FD double prime, which are perpendicular to RA RB, RC, and RD, respectively. Now what's the moment? The moment, M, is PL, which is going to equal the sum of the contributions of all of those F double prime forces about the centroid. So there's going to be an FA double prime times RA plus an FB double prime times RB, and so on. Okay, so M is equal to P times L, which is FA double prime RA plus FB double prime RB plus FCR double prime RC plus FD double prime times RD. So that's the moment about the centroid. Now we said that F double prime was proportional to the distance from the centroid. So suppose I wrote FA double prime and I wanted to compare it to FB double prime. Well, if bolt A was twice as far from the centroid, then RA over RB would be 2, and FA would have twice as much force. And I could make a similar comparison of FB double prime. I could just invert this and compare FB double prime to FA double prime. And similarly, I could say that FC double prime is RC over RA times FA double prime. I could express all these F double prime forces in terms of FA double prime using that ratio of radiuses, essentially. Okay, now if I substitute all these into the moment equation, let's see, M was equal to FA double prime times RA plus FB double prime times RB. Well, if I put in RB over RA times FA double prime, if I put that in for RB, okay, so I'm taking that and I'm putting it in there, and I get this term. Okay, so that's FB double prime times RB. And I'll make the similar substitution for the other forces, FC double prime. And I'm going to have FA double prime showing up in all of these expressions. And the final one, FD double prime, is RD over RA times FA double prime times RD. Now I can pull out FA double prime from here, and let's see, I'm going to have, if I were to multiply both sides by RA, I'd have RA times M there, I'd have RA squared there, and I'd end up getting rid of all those RAs on the bottom. So now when I pull out FA double prime, I can see that I'm going to have M times RA in the numerator, and I'm going to be left with RA squared plus RB squared plus, I got RC times RC squared plus RD squared. And so that's the basically the formula that was on the previous page. And in general, for any rivet or bolt labeled I, Fi double prime is going to be the moment times the distance of that bolt from the centroid times the sum of Ri squared. Let me do a better sigma for you here. There we go. That's the sum over I of all the radii squared. And using the numerical values in this example, Ri is equal to L over root 2. So what do I get? I get all of those Fi double primes to be equal to. The moment was PL. Ri over, basically in this example, the sum of all the Ri squared is going to be 4Ri squared. My Fi double prime PL over 2 root 2L, which is equal to 4,500 newtons times a 0.5 meter moment arm over 2 root 2 times L was the side of my bolt pattern square, 10 centimeters. I get 7,955 newtons. I don't need that anymore. All right, so that's the each of the 4 rivets creates 7,955 newtons, which opposes the moment due to P, which tends to rotate that top plate. Okay, now I got to look for the critical rivet here. All right, I got to add these F primes and F double primes vectorially. Okay, here for A, I can see that FA is down and FA prime is down and FA double prime is kind of uppish. The resultant of those is going to be a little bit of, I guess you might say, a sort of a cancellation there. On the other hand, FD prime and FE double prime, also FB prime and FB double prime, they're both kind of downish, and I can see the resultant using tip to tail is going to be longer. Alright, so I'm going to use either B or D. Both will give me the same magnitude of the vector sum of the 2 forces in this case. So we'll go back down here and we'll finish this off. Go back to the blue pen. We have the highest vector sum of F prime and F double prime at B and D. Alright, so if I pick B for example, I said I had 1125 newtons going down. Actually at B, I think I had it that way, 45 degrees. And the magnitude of those we said was 7,955 newtons. So I can add those vectorially. FB total, it's going to be the root of all the horizontal components squared plus all the vertical components squared. Alright, horizontal components, I got 7,955 times the sine of 45 squared. And the vertical component, I will have 1125 down and 7955 cos 45 down. Square that, put it under the square root, and I'll get 8,787 newtons. Alright, so now the goal was to find the diameter, and we were told that we are having a safety factor of 2. So I'm going to set my maximum allowable stress to be my shear strength divided by 2. And the shear stress is going to be the force, total force FB, divided by the area, which is based on the nominal diameter of the rivet, pi d squared over 4. Okay, so I had 65.25 MPa as my shear strength divided by a safety factor of 2 equals FB 8787 over pi d squared over 4. Solving for the diameter, I get 0.0185 meters, so 18.5 millimeter diameter rivets. Alright, so to summarize, certain joints you're going to have a direct shear, and if the load is offset from the centroid of the bolt or rivet pattern, there's going to be an additional component of force which is going to create that moment M. Those forces will be perpendicular to a line from the centroid of the bolt pattern, and the magnitude of those F double prime forces will be proportional to the distance from the centroid.